All right, before we go back into section 7.1 in the notes, I would like you to pull out 7.1c, which was your assignment, and I'd like to go over problem number 17 with you, just to make sure you're on the right track with how to do those problems 17 through 22. All right, so 17, the directions say find the area of the right triangle with given leg L and hypotenuse H, round decimal answers to the nearest tenth. So 17, we have a right triangle. We're told that the hypotenuse is 19 and one of the legs is 13. It doesn't matter which leg we label 13, so I'll just label that leg 13. We know that area of a triangle is 1/2 base times height. Area equals 1/2. Now remember, in the previous video, I said that the height of a triangle is always the perpendicular height. Well, the perpendicular height is right here. So we have that, and that is 13. We have the height, and now we just need the base. And the base is going to be right here. So we're going to have to use the Pythagorean theorem to come up with that base. 13, 19, that's not one of our common parents, so we're going to use Pythagorean theorem to solve for that leg. So we'll call that leg A. We could have called it B, it doesn't matter. So we know that A squared is going to equal C squared minus B squared. So A squared will equal 19 squared minus 13 squared. 19 squared, that is 361. And 13 squared, that's 169. 361 minus 169 is 192. Take the square root, take the square root. Now, I know that the directions said to give you the decimal answer, but I'm going to show you what the exact answer would be, and then I'll also show you what the decimal answer will be as well. So I want to simplify this radical. To begin with, 192 is not a perfect square. So we simplify 192, and I know that 16 is a perfect square, and it goes into 192 12 times. The square root of 16 is 4. Now 12 can still be simplified. That would be the square root of 4 and the square root of 3, and the square root of 4 is 2. So in between here is all multiplication. 4 times 2 is 8, so A equals 8 times the square root of 3. A is 8 times the square root of 3, so that is this side of the right triangle. So area equals 1/2. Now our base is 8 times the square root of 3 times 13. So this is really area equals 1/2 times 8 times the square root of 3 times the square root of 13. So we can just multiply going straight across. And remember, multiplication is commutative, so we have 1/2 times 8, so that is 4 times the square root of 3 times 13. Now, 4 times 13, I can rearrange this because once again multiplication is commutative, so we can do 4 times 13, that is 52. So the exact area would be 52 times the square root of 3. And when we do 52 times the square root of 3 on your graphing calculator, we get the area rounded to the 10th is approximately 90.1, and that's going to be centimeters squared. And that's centimeters squared. So this answer here, this is the exact, and this answer here, this is an approximate, as the direction stated, rounding it to the nearest tenth. So I wanted to show you both ways there, the exact, how to get it exactly, and then how to get the approximate way, right? Because you're going to have to know how to do both. So that's how problem number 17 through 22 should have been approached. So if you had any trouble with 17 through 22, now you can use this as a model to go through those problems. So right now what I'd like to do is I'd like to pick back up in your notes in section 7.1. In the previous lesson, we looked at the Pythagorean theorem, and we looked at those Pythagorean triples. Okay, those parents, the 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. And we looked at how to generate more triples from those parents. Now today, we're going to look at the back half of section 7.1, and that's the hypotenuse-leg theorem. So opening up to that theorem in your notes, this is theorem 4.5, hypotenuse-leg theorem. And it says, if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle, then the two triangles are congruent. And just so you all know, yes, I do realize that I have the word theorem up here twice in the name. That was a typo on my part. So once again, if the hypotenuse and the leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle, then the two triangles are congruent. So this theorem is another justification for us to prove triangles congruent. So to prove triangles congruent, just a reminder, we have angle, side, angle, side, 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 and angle, angle, side. Now adding to that, we have hypotenuse leg, which is abbreviated HL. Now, hypotenuse leg only works with right triangles. So this is a very key part here, right triangle, meaning that you have to state that the triangles are right triangles before you can use this theorem. Must state triangles are right prior to using theorem. And the reason for that is very simple. If you look up here at the picture, you can see that we have AC congruent to FD and AB congruent to DE. And then we have angle C and angle F. Those are the right angles. They are congruent. Well, if I look at this, since it's a right triangle, hypotenuse leg, it's actually angle, side, side, angle, side, side, which we know doesn't work. All right, that does not always work. So that is why it's not a theorem. We talked about that as we went through chapter 4 with the triangle congruencies. So that doesn't always work. That's not one of our justifications to prove triangles congruent. However, in a right triangle, it does work. And we call it hypotenuse leg. Because in a right triangle, what we know about right triangles is that that right angle is always going to be there. The right angle is always going to be there. Right angles are always congruent. We have a theorem that says that. And now all we're saying is, all right, if we have a leg congruent and the hypotenuse congruent, now we know the triangles are congruent. So turning the page in your note packet, or staying on that same page, excuse me, sorry, staying on that same page, we're going to be looking at the if-then proof for this theorem. So we're on that same page as hypotenuse leg theorem. And the if part of that theorem. If we look at the if part, it says if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle. So I'm going to draw two triangles, triangle ABC and triangle DEF. And we're told that they're right triangles. So we're given that triangle ABC and triangle DEF are right triangles. And we're also told that AB is congruent to DE and AC is congruent to DF. And we want to prove that triangle ABC is congruent to triangle DEF, because if we look at the then part of the theorem, it says then the two triangles are congruent. So if we have this set up in the if picture, then we can say triangle ABC and triangle DEF are going to be congruent. Okay, all the triangles and all the corresponding parts are going to be congruent. So looking at the proof for this. statements, justifications. And we'll start with the given. Triangle ABC and triangle DEF are right triangles. We know that segment AB is congruent to segment DE, and segment AC is congruent to segment DF. That is given to us. Okay, next step. Now, if we want to get these two triangles to be congruent, we can't use hypotenuse leg. So the options that are available to us, we have side, angle, side, angle, side, angle, side, 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 and angle, angle, side. Based on the picture and what we're given, which one of those four do you think it's going to be, or which ones can we eliminate? Well, if I look at the picture, I see we have AB congruent to DE, we have AC congruent to DF. So we have two sides. So that eliminates angle, side, angle, and angle, angle, side. We have two sides. I'm thinking that eliminates those two, or at least that's a good thought and a good way to go about it. And in addition to that, we know that B and E are right angles, but they're on the outside of it. So in terms of getting that interior angle, which would be A and D, that'll probably be somewhat difficult. So we're probably going after side, side, side. Now, what do we know about right triangles? We haven't studied that much about them. If you look back in your Chapter 7 notes, we only know one thing about right triangles. And what we know about them is that the square of the hypotenuse is going to equal the sum of the squares of the legs. That's the Pythagorean theorem. That's all we know about right triangles, other than they have a right angle. So that's all we can do. We have the Pythagorean theorem, which tells me AB squared, that is a leg of triangle ABC, plus BC squared will equal AC squared. That's your Pythagorean theorem. Next step. We know the same thing about triangle DEF. We know that DE squared plus EF squared equals DF squared. So if I look at this, all I have in here are side lengths. That's all I have. We have AB, BC, AC, DE, EF, and DF. That's all we have in the proof. So I know that side, angle, side is not going to be a possibility. We are going after side, side, side. We need to get all sides of these two triangles congruent. So essentially, we need to get what we're going after is BC congruent to EF. And if I want them to be congruent, I know that I want them to be equal first. So I want to get BC and EF equal. Well, looking at the proof, where are BC and EF located? Well, BC is right here in step 2, and EF is right here in step 3. So the first thing we need to do is we need to get them to be on the same line. Right now, I see AB plus BC, sorry, AB squared plus BC squared equals AC squared. And DE squared plus EF squared equals DF squared. I know something about these two. They're the hypotenuse of each triangle. And I know that the hypotenuse are congruent. That was given to us. So, AC is congruent to DF, which means AC equals DF. Definition, congruent segments. And now that they're equal, that means I can take DF out of step 3 and put AC in its place. So that's what I'm going to do in step 5. DE squared plus EF squared equals AC squared. That's substitution. Steps 3 and 4. Now, looking at steps 2 and step 5. Step 2 and step 5. Both of the legs are being added together, and they both equal a squared. If you look here, we have it equal to a squared. Here, we have it equal to a squared. So we've done this many times this year. We can now use transitive to say that ab squared plus bc squared equals de squared plus ef squared. Transitive. Well, we now have BC and EF on the same line. They're in the same step. They're in step 6. Now all we have to do is figure out how to get rid of AB and DE. But we know that AB is congruent to DE. So since they're congruent, that means they're also equal. We're told from the given that AB is congruent to DE, so now we make them equal. Now that they're equal, I can take DE out of here and replace it with AB. AB squared plus BC squared equals AB squared plus EF squared. That's substitution. Steps 6 and 7. Step 9. We can now subtract out the AB squared. And we get, subtract AB squared from each side, we get BC squared equals EF squared. And that is subpo. Subtracting AB squared from each side. We now take the square root of each side. BC equals EF. That's definition of a square root. Taking the square root of each side. And now that they're equal, that means segment BC is congruent to segment EF. Definition, congruent segments. And now that they're congruent, that means that the two triangles will be congruent. Triangle ABC is congruent to triangle DEF, and that is side, side, side. So, in that theorem there, we were able to use the Pythagorean theorem, the one we studied in the previous lesson, and this proof proves the hypotenuse leg theorem, which is another justification that allows us to prove triangles congruent. So we now have 5 justifications to prove triangles congruent. Side, 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 angle, side, angle, side, angle, 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 side, and in right triangles, hypotenuse leg. And remember, it is important that we state that it is a right triangle, because if you look up here in the given, we stated that triangle ABC and triangle DEF are in fact right triangles. Okay, moving on in your notes. This next proof in your notes packet, I want you to put a star next to it, and you're going to complete that tonight as part of your assignment. And I want to go to the next proof in the packet, and we're going to work through this one together. If you'd like to, we're not going to do this as a paragraph proof. So if you'd like to pull out a sheet of proof paper, you can, because there's not a lot of room on the bottom of that, and you probably won't be able to fit it on the bottom of that page. So you can pull out a piece of proof paper or go get some on the counter. So, starting this proof off, two columns. Statements, justifications, start with the given. Our given is that GH is congruent to KJ. FG is congruent to LK. And angle FJG and angle LHK are right angles. And we want to prove triangle FJK congruent to triangle LHG. So triangle FJK is this triangle right here in blue, and GHG is this one here in blue. So if we look at what we have here, we need to get these two triangles to be congruent. If I look at the other two triangles, though, in this proof, now there are a lot of different ways you can do this, but two triangles jump out to me immediately in this proof as, oh my gosh, you know what, I think we can get these two triangles congruent because of hypotenuse leg potentially, because the right angles are staring right there at us. And that is triangle FJG and triangle KHL. And when I look at those two triangles, and I think we can get those to be congruent by hypotenuse leg. And once we get those two triangles to be congruent, so what I'm proposing, so that we're all on the same page, is we get triangle FJG congruent to triangle LHK. Getting those two triangles to be congruent, they're highlighted up there in yellow. Once we get those two triangles to be congruent by hypotenuse leg, so the hypotenuse for each triangle is here and here, and then this leg here and this leg here, because HG is congruent to KJ, and this JH overlaps. So I'm thinking we can probably get hypotenuse leg with those two triangles to get them to be congruent. Now, once they're congruent, what does that allow us to do? Once they're congruent, that means FJ is congruent to HL. So now we have two sides of those two triangles congruent. And we can get that to be a right angle and that to be a right angle. That will give us side angle side with the two triangles there in the blue. So hopefully you all just followed what I did there as I talked through it, but that's what we need to start thinking about as we start going through these proofs. You know, how do you get from point A to point B? And all the steps that need to be in between there, and how do you look at a picture? Now, there were a couple other ways to do this, so that was not the only way, but that's how I'm going to be proceeding here. So we know that KJ is congruent to HG, and I want to get KH and JG into the proof. I know that KJ plus JH equals KH. That's segment addition postulate. And then we know that GH plus HJ equals GJ. Same justification. We know that KJ and GH are congruent, so that means they're equal. And now that they're equal, I can take this GH out and put KJ in its place. So KJ plus HJ equals GJ. Substitution. Steps 3 and 4. From here, we can run transitive. We know that GJ is equal to KJ plus HJ, and KJ plus HJ is equal to KH. In steps 2 and 5. So if you look at steps 2 and 5, we have transitivity there. So that means KH equals GJ, transitive. And now that they're equal, that means they're congruent. Definition, congruent segments. Hopefully, as I'm going through this, you're all seeing where this is going. So we now have JG from here to here congruent to KH from here to here. So if I look at the two yellow triangles, we now have them congruent by hypotenuse leg. But there's just one last thing we have to add. Remember, before we can use hypotenuse leg, we actually have to state that they're right triangles, because we never did that. We know that we have right angles in them, but we need to state that they're right triangles. Because when we look back at the theorem, it says of a right triangle right there. So we want to make sure we state that we have a right triangle. So going back down, step number 8, triangle FJG and triangle LHK are right triangles. That's the definition of a right triangle. And now that they're right triangles and we have the hypotenuse and the leg congruent, we can say that triangle FJG is congruent to triangle LHK, and that's hypotenuse leg. So those two triangles are now congruent. So that means that FJ is going to be congruent to HL by CP/CTC. So now we have two segments in the blue triangles congruent. Now we just need to get this included angle here and here to be congruent. Well, we know that FJG is a right angle. So that means that FJ, segment FJ and segment KG, since FJG is a right angle, what do we know about FJ and KG? FJ and KG are going to be perpendicular because it forms a right angle. And that's the definition of a perpendicular line. Remember, definitions work forwards and backwards. So perpendicular lines form right angles, and right angles form perpendicular lines. So FJ is perpendicular to KG. FJ is perpendicular to KG. Definition, perpendicular lines. And we know that LH is perpendicular to KG. Same justification. Now that those are perpendicular, we know that this angle, angle FJK, is going to be a right angle. Because if FJ is perpendicular with KG, then the definition of perpendicular lines, once again, tells me I have a right angle. So angle FJK is a right angle. Angle FJK is a right angle. And that's the same justification definition of perpendicular lines. Then angle LHG is also a right angle. And it's the same justification, definition of perpendicular lines. So, because FJ is perpendicular to KG, we got angle FJK to be a right angle. And LH is perpendicular to KG, we got angle LHG to be a right angle also. Now, looking at steps 13 and 14, both of those angles are right angles, and we know that right angles are congruent, so angle FJK is congruent to angle LHG, right angles congruence. So FJK and LHG are right angles, they're congruent. So those angles right there are congruent. So we have side angle, side. The two triangles are now congruent. So triangle FJK is congruent to triangle LHG, side, angle, side. Okay, your assignment is to complete the proof in your note packet that is above this one. Okay, that concludes section 7.1.